My name is Steven. I'm with FoundationDB. We're in Tysons Corner, Virginia, just outside of Washington, D.C. And all the slides in this presentation and the code behind them and an IPython notebook with more detail is on my GitHub here. So if there's something you see that I went by too fast, feel free to go ahead and grab that. And what FoundationDB does is produce a distributed key value store that I'll be talking about, and in particular the Python binding for that today. There's a lot of different alternatives for data storage. When you have data that's too much to store in memory, or you want to store it durably, there are Python-specific tools like ZODB or PyTables. Obviously, there are SQL databases, SQLite, MySQL, Postgres. There's various ORMs, SQL Alchemy we've heard about in a couple of different talks. And there's a lot of newer NoSQL alternatives, document stores, graph databases like Neo4j, and key value stores. So FoundationDB is a key value store. And what do we mean by that, just so we're all on the same page? Well, it's very simple. The basic data model is that keys map to values, very much like in a Python dictionary. And it's really the simplest data model that's used by other databases. Used by databases in general, but it's used under the hood in a lot of databases that expose some other model. So for example, in SQLite 4, even though it's exposing an ANSI SQL relational database, underneath the hood, what it's actually doing is mapping that data to a key value store. And in SQLite 4, they've actually exposed that, so you can poke at that and see that. But that's really true of almost every database, whether they expose it or not. That before the data is actually hitting disk, when it's going to B trees or whatever, there's something very much like a key value store there. So how does FoundationDB relate to that? Well, FoundationDB runs on distributed clusters. So it's a distributed key value store. It's meant to be scalable, performant, fault tolerant. And it exposes a single logical key space. And it is ordered. It has the ordering property that makes range reads very efficient. And that also has a very strong effect on what you can do in terms of data modeling. It also supports full ACID transactions. And these two things, the ordering property and the ACID transactions, allow you to easily build rich data models. We'll talk a bit about that. So just so we're on the same page, ACID, what does that mean? The property is atomic, consistent, isolated, and durable. And these are basically the essential properties of transactions, of any operation where you're writing or reading from the data store. So the isolation property, for example, there's various levels of isolation that are possible, but FoundationDB supports a very strong sort of isolation called serializability. And what that means, in effect, is that every single transaction is guaranteed to be executed as if it were sequential. Even though, in fact, you may have many, many clients writing concurrently, the logical effect of each write that commits is guaranteed to be as if there was some full ordering on those transactions. And this is a really powerful property because it allows you to reason locally even though your clients are reading and writing globally. And by locally, I mean when you're writing code local to a specific transaction or function. And so this means that any invariants that are maintained sequentially in your function are guaranteed to still obtain under concurrency. So the impact of any particular client is isolated. So a simple example of preserving invariants, you may have some sort of operation that's storing people's names and social security numbers, and obviously they need to be associated. And you may have a method or a function that gets the name from the social security number, and another that gets the social security number from the name. And obviously an invariant that we would like is that if you get a name from a social security number of that given name, that you're going to get back the same thing. Well, you can easily imagine concurrent scenarios where lots of different clients are writing where that can get corrupted, and you're not going to get back the same thing because a name was changed but the social security number remain the same or whatever. But the point is, if you write the code correctly so that it works sequentially with ACID transactions, you're going to inherit that property even when it's concurrent. And this enables you to build up larger, more complex, stronger abstractions. So you can imagine some application that's maintaining a leaderboard where scores are getting updated from players with a lot of different games from a lot of different clients, updating a database concurrently. And you may have some function that updates the rank of a player when a new high score is established. So you write this simple function, and what you would do in FoundationDB is there's a decorator, FDB Transactional, that basically says this function is to be executed as a transaction. And once you do that, you're guaranteed these properties. And it allows transactions to be defined by you. It's not simply some set of pre-canned compare and set operations that it can act on a single row or something like that. You can define these over multiple keys. They're touching data that may live on multiple nodes throughout your cluster. And that's sort of transparent to you. What it looks like you're writing is a simple Python function, and all the rest you get kind of for free. So the big deal with this is that it allows you to support multiple data models. The ordering property combined with the ACID transactions allow you to write at the Python level graph, column-oriented, document, relational, various sorts of data models, and have them all stored together in a single database on a single cluster, so you're not maintaining separate silos. And just as an example, one of several, we actually have a SQL layer which supports full ANSI SQL with all the DDL and everything you would expect. It's all getting mapped down to the key value store, and that can coexist with a document layer or other sorts of things. So how does this look in Python? How does this get exposed in the Python binding? Well, the abstraction is incredibly simple. It's so simple that when you look at the code, it's like, well, where am I doing the database stuff almost? So there's a DB, which is the database, and it's a mutable mapping from keys to values. It's ordered. So in Python terms, it's sort of like a sorted dictionary, not an ordered dictionary. The ordered dicts in Python are recording the order of the key insertions. This is more like a sorted dictionary where the ordering is defined on the sort order of the keys. And all reads and writes to the database are through transactions using very familiar Python syntax. So a transaction simply has a snapshot of the database, and it allows you to do reads and writes on that snapshot. So here we have a write. We're assigning the value read to the key apple. Then we're going to do a read. And this third one is a range read. So the range of keys, whatever is falling between apple and pear, we're going to pull back all of those values within that range. So a very familiar Pythonic syntax, almost looks like you're working with dicts, using subscripting and the sort of slice syntax. But those are actually transaction objects. So a transaction is always performed as a unit. That's the ACID property of atomicity, independent of all other transactions. That's the isolation property. And it gives you a building block for data modeling, even under very high concurrency. When you're working in a transaction, FoundationDB works to maximize the concurrency consistent with the order of your own operation. So for example, if you had this code here inside of some larger function, you're doing a read on some key A and a read on a second key B, and then you're going to do a print on the concatenation of A and B. And you can, sort of as a first approximation, you can think of those little a's and little b's as being strings that you're just going to concatenate. But in fact, they're actually futures. If you've worked with futures in Scala or anything like that, it's the exact same concept. So that initial read returns immediately, and gives you a future. You're not waiting on the database latency, whatever it actually took to go out to the database, perform the transaction, do whatever conflict checking is necessary, and bring back that value. You're getting a non-blocking operation that returns immediately with a future. And then you can go on and do many, many more reads. You could do 100 reads, all of them like this. It's only going to block when you actually need the value, such as when we do this concatenation. So it's implicit blocking. All the latencies of the reads get overlapped. So should talk a little bit about conflicts and retries. Some of how the magic works is we use optimistic concurrency, which means all transactions proceed until you attempt to commit. Until commit time, everything is just going to proceed as if there's no possibility of conflict. You're just going to go ahead and do it, and it's fine because you're only acting on that local snapshot. When you attempt to commit, then there's conflict checking, and the system is going to check if any other transaction has written data that you have read and therefore possibly invalidated your operation. If so, your commit attempt will fail. And what happens is the client, in the usual case, the client simply retries that transaction. Real quick question? Go ahead.
So in the previous example,
I didn't even commit here.
Okay, so what happens if someone changes before you print? You see the value?
Typically, what you would really, if the print is obviously a side effecting thing, you would actually be careful and return that value out of your transaction before printing. So here I've simplified and I haven't even bothered to commit, but you would usually do your commit first. Okay, so the transactional decorator I mentioned earlier, basically it takes a function and it encapsulates it in a standard retry loop. And so I mentioned you have to retry if your commit fails. Well, the decorator is actually going to do that for you. So you don't typically write retry logic yourself. You can use the decorator, and it's not simply retrying in a loop. It actually has exponential backoff built in. So it's doing some fairly sophisticated things. And it makes it very easy to define transactions, but also to compose them. So here's an example that I'll talk a little bit more in subsequent slides, but imagine an object store where you're reading and writing sort of object data, and this is a merge object function where you're going to take a bunch of fields and values and merge them into an existing object, and inside it's going to call set value. Set value is some other function, transactional function that you've defined also using the decorator. I just haven't shown you the definition here. Basically, all or none of the writes from merge object, when you go to commit, will be performed. That's the property of atomicity. Either the commit's going to succeed and they'll all be performed, or none of them will happen and they'll all be retried. So you can compose transaction this way 2, 3, 4 deep as much as you want, and exactly what you think should happen from looking at it is what's going to happen. The composition just works. Okay. Let's talk a bit about Keyspace in FoundationDB, how it's organized. Keys are simply byte strings. Keys and values are both byte strings. They're all ordered in the obvious way. Now, obviously, when we work with data, like in Python, we typically don't want to work exclusively with byte strings. That would be rather unpleasant. So the binding exposes a lot of richer ways to work. There's what we call the tuple layer that allows us to represent data in tuples. And there's a notion of subspaces that allows us to hierarchically structure Keyspace. And it allows you to take various Python data types, write them to the database, and get them back in a kind of straightforward way. So the tuple layer allows you to define compound keys using Python tuples. And the tuple layer has methods that automatically translate between the tuples in bytes. So here, for example, you may be working with graph data, and you want to define an edge from node 1 to node 2. This would be one possible way to do that. You're simply using strings here, and those all get packed into a byte string that becomes your key. And the ordering property is preserved. So the order on tuples, on just regular Python tuples will be the same as the order on byte strings that are actually written to the database. So when you go to do range reads, the ranges you get will be exactly what you would expect looking at the Python tuples. Subspaces are kind of namespacing for different categories of data. And there's a subspace class that has you give it a prefix, 10 minutes, thank you. And it lets you structure data that way. So the subspace is basically a Python sequence that you can use subscripting syntax with. So this would be an equivalent write to the one we saw earlier, with a little bit smoother syntax. And there's a directory capability that allows you to automatically allocate prefixes for subspaces, and it allows blocks of data to be moved very, very efficiently. And it's simply moving basically a pointer, not the whole set of data. So in Python, you typically have data represented as you normally would, using whatever data types, and you often want the data to be stored in some form, like a vector, a graph, tables, what have you. The technique we use in FoundationDB is to map that to the key value store, taking advantage of the ordering. So you may have an object store where this is I'm imagining here a very simple object store with data held in dicts, not something sophisticated using classes like in SQL Alchemy. Basically, dictionary structured data that you want to write down to the object store. And as a first cut, thinking about how would you store such a thing in a key value store, you might think of serializing entire objects, pickling it, using JSON dumps, something like that. And that is very simple, but it has a lot of limitations in that you can no longer access individual fields, and you can't index individual fields within those objects. So that's kind of a bit of an anti-pattern. What we typically do is take an object like that and split it up into a set of keys and values and write out the individual keys and values. And that allows you to get to fields much more efficiently. So this kind of a picture, if you imagine a dictionary on the left, that's going to get translated into a bunch of keys and values on the right, representing the keys in their tuple form. Okay, so you can look at the code on GitHub and see an example of how this works, but we can have single-valued fields, multi-valued fields, we can index fields, and it's all a matter of taking advantage of the ordering of those keys in the database. So there's the key value store itself exposes no query language, but it turns out that it's very easy to query the data simply using the tools that Python gives us. We can use generators, itertools, comprehensions to very efficiently munge this kind of data. In the example object store that I have on the GitHub, I use generators to, whenever there's a method that ranges over a set of objects and returns the result, what it's actually returning is a generator that will return the results one by one. Much more efficient than actually building a list in memory. I'm sure many of you are familiar with that technique. So an example would be get by value, where you're supplying a field and a value, and you want to get back all of the objects that actually match that field and value. If you have indexed the field, then this actually translates to a single range read. So you could be getting back some very large set of objects, but you're actually just doing a single read on the database to do that. So I have some examples where I've loaded up emails from the Enron email corpus, represented them as objects, stored them out, and taken a look at how to do queries on them. The translation of emails to objects is pretty simple. Each person becomes an object with their email address as the primary key. Each email message is an object. And then there's a field sender that says person sent this message. It's indexed and it's multi-valued because a person can send multiple messages. That's what the M and the I indicate. So some simple queries, how many messages were sent. You simply do a get by field. The field is the sender field. That's going to produce a generator sending back those objects. And we want to count them. We can't simply use len on a generator, but ilen is a simple equivalent. You can just take a generator expression, feed it to the sum operator, and you will get a count of them. Of course, the disadvantage of that is that consuming a generator consumes the generator. You no longer have it around to consume again. So Ator Tools gives us some nice ways of handling that. Ator Tools has a T that allows us to copy a generator, and an iSlice that allows you to slice a generator much as you would any container. So say I want to show the first 5 messages here. Same query as before, but this time I do a T, and I have the first and second, so now I have 2 copies of whatever is going to come out of that generator. I can do an iSlice, which is the same as doing a slice on a list to get the first 5 elements on the first. But that second copy of the generator is completely unconsumed, so I could begin consuming it again from the beginning. So some more queries. How many messengers were sent by Jeff Skilling? He's the former CEO of Enron. Get value of Jeff Skilling on the sender field is going to give you the emails he sent. This one actually returns them in a list rather than a generator, so here we can simply use len, and it's a simple API call. A little bit more complex with a comprehension. What are the subjects of all emails sent by Jeff Skilling? It simply says, get the value of the subject of the email for all emails sent by Jeff Skilling. This is a good example of, the sort of Python as English, getting fairly close there. What are all emails on which Jeff Skilling was blind copied? Now, this one looks even simpler. Get by value. So the field is blind copy field. The value is Jeff Skilling, and this will return all of those. However, it turns out this is a very expensive query. If you actually pull down the code and run this, you'll see a very notable pause as this one runs. And the reason is we did not index that VCC field. If we were going to do this query a lot, we could simply have make that an index field, and then it would reduce to a single range read. So we have Ator Tools in group by. Other way around. We have group by in Ator Tools, so we can define group messages by sender. Get by field on the sender field will return all the persons and messages they sent. We can group those by the person. Item getter 0, the first one returned is the person. And then we can, that's also a single read from the index because sender is an index field. So then we can use that to say things like who sent at least 3 messages. Simply getting all the persons and their emails and then doing the test if the emails were more than 3. You're going to get some long list of names. We may want to ask, did anyone send more than 300 emails, looking for outliers or whatever number we care about. Again, that's a quite simple query there, using an any operator, a generator expression to an any operator. Who sent the most emails and how many was that? Again, the same group by sender, only now we're doing a max for the sender and the number of emails they sent. And we're passing to that max the key lambda pair 1, meaning that we're going to do the max over the number of the emails. That's getting a little complex there. If we simply want to know the highest number of emails sent, we can simply do that same max without any key simply on the emails, and that'll work just fine. So takeaways. FoundationDB is a key value store. Key value stores mesh very well with Pythonic constructs. When you have transactions and ordering with a key value store, it allows you to implement richer data models in a very natural way. And FoundationDB also gives you this in a very performant and scalable way running on distributed clusters. So thank you very much. Any questions? Any other databases? Well, that covers a lot of territory. So for example, other key value stores like React would have a similar sort of API, although React has very different properties. Other data stores like Mongo, which are document-oriented, or obviously any of the SQL databases are going to be quite different.
So if I have a big web application with Postgres, Redis, and Neo4j, can I get rid of all of them and use this?
We have a lot of clients doing exactly that, using it for consolidation. Okay, if there's nothing about your data that inherently makes you need to use those other systems, you just have them for historical reasons, or someone thought, hey, let's try this, then there is a real opportunity for consolidation there. Anything else? Sure. We actually use parallelization and pipelining fairly extensively in our SQL layer to maximize throughput, where we'll take a query and the actual reads and writes get parallelized quite a lot. So that's using actually our Java API. We have APIs in a number of different languages. We have a Go API that's obviously well suited to that sort of thing. But yeah, pretty well suited. All right, well, thank you.